Welcome to part two of this link budget tutorial. In this part, I'm going to cover a lot more about sort of advanced concepts within link budgets, equations that govern link budgets, um, and just things you need to know. So first, I'm just going to give a quick overview of what a link budget looks like. I'll scroll through the UW orbital link budget. Then I'm going to explain noise temperature, SNR, link margin, modulation schemes, orbital mechanics, and polarization. So the UW orbital link budget is based off the AMSAT link budget tool. AMSAT is this organization that has made and launched amateur radio satellites, and they um, provide this tool for anybody to be able to use to create a link budget. So let me just go to that and I'll come back to the slideshow. So here's the link budget. This is the title page. Nothing important here. When you go to this next page, I'd really recommend downloading this Excel sheet, by the way, because some things are harder to see on Google Sheets. So download this if you ever want to update it and then re-upload it in order to make changes, essentially. So this page gives a lot of instructions on how to use the link budget. I'd recommend going over this before you do any edits. It explains like what cells you should edit, and like what sections you should look at, and it gives some like basic background as well. Okay, the next section. So there's let me just actually quickly overview these sections. So there's a couple of sections here that basically where you give some information about your system. So things like your frequency, your orbit, your transmitters, receivers. So this is kind of all of your input sections. Then the output is these two sheets here, the uplink and the downlink budget, as well as the summary. And then there's these other pages past like antenna patterns that are there just kind of to help you. They're like tools that you can use in order to get information to put in your link budgets. So starting at this orbit page, by the way, there's a lot of comments all throughout this document that explain like where certain data has come from. Whenever you make an update to this document, I'd recommend making comments in this way so that people know what the justification for you putting down certain numbers has been. So this orbit page has some details about kind of like orbit parameters that I'll go over soon. This frequency page covers information about what frequency we're transmitting at and stuff like that. And it calculates something called a path loss. This transmitter page obviously talks about both the ground station and the satellite transmitters. The receivers page talks about the receivers as well as amplifiers. Same thing for the transmitter end. They also talk about amplifiers. Antenna gain talks about the antenna. Antenna pointing losses, self-explanatory. There's also polarization loss, which I'll go over. Atmospheric and ionospheric losses. The modulation scheme. And then we come to the actual important pages, the uplink and downlink budget. So the downlink budget kind of looks like this. Gives you a summary of all of the kind of parameters. So a couple of important parameters to see here. There's spacecraft transmitter power output, line losses, and then finally all of that kind of adds up to give you your EIRP, which you might remember from the slideshow is, or from the video in the previous section. EIRP is basically your effective transmitted power. After that, you have a bunch of losses along the path from your satellite to your ground station. And the biggest of these and the most important to characterize is the path loss. So I'll talk about this in a minute, but it's kind of the loss due to just basically as your antenna, as your signal goes through space, it disperses, and that causes some loss. So there's a couple of different losses. There's like transmission losses, There's this thing called noise temperature, which I'm going to talk about. You have to describe the data rate of your transmission. Um, and then the kind of important part is this thing called EB over N naught. Um, that is the kind of key parameter that you want to optimize. This line here gives the EB over N naught that you get for your system based on all the parameters that you put in. And then based on like the demodulation method and some other things, you also select a threshold for what the EB over N naught should be above in order for you to actually do a transmission. So basically just subtracting like this number from this number gives you this thing called the system link margin. And this is the most important parameter that comes out of a link budget. And this is basically what you're trying to optimize in order to get a system to work. Okay, so more details on that in the slides. Just to give a recap, some important things to remember are link margin, signal to noise ratio, and EB over NO, path loss, polarization loss, and modulation schemes. These are kind of what I'm going to cover. Okay, the first most important concept to know about is a path loss. So path loss is basically the loss that your signal experiences as it goes from a focus signal to kind of dispersing out as it travels across space. This is a really good illustration of how that kind of works. You can kind of see as like your signal disperses, the kind of conic angle that you cover gets, well, the conic angle stays the same, but the area that you cover um, based on that angle gets larger. So you have um, kind of loose way of saying it is more area and the same amount of signal. So you have a lower signal strength. Um, so that's kind of an intuition as to how path loss works. Path loss is primarily based on your minimum elevation angle. And what that is the angle at which your satellite is able to reliably communicate with your ground station. And again, that's a bit of a circular definition because one of the things we're trying to get out of this system is, or this like link budget is, when are we able to reliably communicate? So initially, when you kind of give estimates for this path loss or for this elevation angle, they start out kind of arbitrary and then you iterate to get something more concrete. Um, but yeah, the elevation angle is based on horizon clearance in the area that you set up your ground station, the link budget itself, so like, you know, kind of your hardware, and then the orbital path is like a big thing. So yeah, I guess that's the circular definition thing I was talking about. So here's a kind of illustration of what the minimum elevation angle should look like once this page opens. This illustration from the AMSAT link budget gives a good idea of what the elevation angle looks like. So the elevation angle is this kind of distance, sort of the angle from your horizon, or like kind of the perpendicular to the center of the Earth, to the angle at which you're reliably able to communicate with your satellite. Um, so you can see how elevation angle affects this parameter S, the slant range. That's the distance between the satellite at its furthest point, and then your ground station. Um, so as you like increase this elevation angle, the spacecraft gets closer to the ground station. So basically that way your link budget tends to have a higher link margin, but that comes at the cost of less time over your ground station to reliably transmit. So this is one of the parameters you have to tune when you work with a link budget. So again, path loss is based on the geometry of how the signal fades as distance increases. So it's proportional to the wavelength, and it's inversely proportional to the square of the distance from the source point. Um, So those are just some things that are useful to know. This is the equation for it. You don't need to know the equation. It's just for your understanding. The next important thing to understand is noise temperature. Noise temperature is a little bit of a complicated concept when you first try to wrap your head around it. But essentially, it's a combination of noise caused by thermal energy within an environment and external radio interference from your surroundings. So it kind of combines those two sources of noise and characterizes it with a temperature value, which at first doesn't make a whole lot of sense, but essentially the way you can think about it is thermal energy within the environment can tend to cause basically electron conduction within an antenna after a certain amount of time. This is known as John Nyquist noise. You can read a bit more about it. Um, and basically, like I said, you also have some RF interference from like other sources like radio stations and things like that. So what noise temperature is it's kind of taking the noise from both of those sources together and coming up with an equivalent temperature that your surroundings would have to be at in order to cause that power of noise. Um, so noise temperature is related to the power of the noise with this equation, where the power is of the noise is this, the bandwidth is B, this is Boltzmann's constant, and then this is the noise temperature. Um, so essentially, it's kind of like your noise power per hertz of bandwidth. Um, Noise temperature is based on both your surroundings and your antenna's radiation pattern. And you can use this kind of like, I mean, you don't actually use this equation, but this is kind of the theoretical formulation of noise temperature with like a double integral. It's essentially kind of the uh, integral of the noise multiplied by your radiation pattern. It's like essentially a weighted average of the temperature in your surroundings. Yeah. Next thing to understand is SNR and E sub B over N naught, which for the purposes of this presentation, I'm going to call EBNO. And then also link margin. So SNR and EBNO are like the two, they're basically the same thing. So I'm just going to talk about SNR first. SNR is the signal to noise ratio. It's essentially the power of your signal divided by the power of your noise. And in a link budget, this is kind of what you're actually trying to optimize in the end. So essentially just simply increasing the transmit power of your transmitter or doing something like that isn't always necessarily going to help your link margin at the very end. What you need to do in order to actually optimize signal to noise ratio um, is find ways to increase the pure signal without also increasing the noise embedded within the signal. So um, when you use a for example, a low noise amplifier at a receiver within a communication system, one like important thing to realize is that a low noise amplifier on its own typically doesn't actually um, increase the SNR because amplifiers typically have some noise of their own that they add to the signal. So using an amplifier is actually sometimes not the best choice in order to get a better signal strength. Those are some things to like look at when you're building a link budget and kind of keeping in mind that just the absolute power of the signal is not the important thing. EBNO is basically a little bit of a more complicated version of the SNR. It takes into account the transmission rate that you transmit at and calculates essentially an energy per bit. that is within your signal. And then it's kind of like a ratio of the energy per bit divided by the noise per hertz of bandwidth within your signal. I won't go into too much detail about that. You don't necessarily need to understand exactly what it is, um, but this is like a good intuition that I think you should have. All of this stuff comes from something called the free transmission equation. The Notion page has a pretty detailed breakdown of kind of how this is derived, and it kind of explains how your signal power is basically the sum or like the product of your transmit power and then several gains and several losses within your system. I'd highly recommend giving this page a scan before diving into the link budget. So all of this leads up to link margin, which is, again, the parameter that we were actually trying to optimize out in the end. So link margin is a difference between, it can be calculated for either EBNO or SNR. And you'll see in our link budgets, it's actually calculated for both versions. I'd recommend using the EBNO version for our purposes. So link margin is basically the difference between the achieved and the desired EBNO. It's very simple. It's actually a ratio between the achieved and desired. But since it's given in dB, it's basically like a subtraction between if you know basic log rules, you know that a division is equal to a subtraction in a logarithmic scale. And since dBs are a logarithmic scale, it's essentially a dB difference between the achieved and desired EBNO. Your link margin for CubeSat should be ideally 10 dB. But in order to establish communication, you should aim for at least 3 dB in most systems. This is just to account for any potential losses that come up in the system after you've launched it, things that you can't predict. It just gives a little bit of margin for you to be able to actually be sure that you can still transmit. Okay, the next thing to talk about is modulation schemes. So this is a pretty important topic in communication theory in general. When you send a radio wave, you send essentially something at a set frequency, but you can't encode data into that radio wave unless you somehow alter that wave in order to encode data into it. So there are three main ways of encoding data into a wave. One is phase modulation, which is shifting the phase of the signal left or right to encode some information. So just causing these like instantaneous phase jumps to create an encoding of ones or zeros. And then there's the more commonly known frequency modulation FM and amplitude modulation AM. You might know those from when you're using the radio in a car. So frequency modulation is obviously increasing and decreasing the frequency of a signal. In radio, it's kind of done with sound, which is like a wave on its own. So it's a little bit different from the way that it's done in CubeSats. CubeSats usually typically use something called frequency shift keying, which I'll talk about in a second. AM is not really used in CubeSats. PM, phase modulation, is sometimes used, but it's more for typically used for more expensive satellites that are transmitting in deep space. So CubeSats use frequency shift keying, most CubeSats at least. So the way that FSK works is it's very similar to regular FM radio, but instead of encoding sound, which can have kind of it has its own, sound has its own like bandwidth and like it's like a wave and it's like a little complicated. FSK is much simpler. It's just basically increasing or decreasing the frequency to encode a 1 or a 0. You can see kind of in this example, when you pulse a 1, the frequency is a bit higher. When you pulse a 0, the frequency is a bit lower. So you hop between these two frequencies. So There are some other versions of modulation schemes that use more than just ones and zeros. For example, instead of hopping between two frequencies, you could hop between four different frequencies, and that would allow you to represent two bits. So for example, a frequency F1 could be 0, 0, frequency F2 could be 0, 1, frequency F3 could be 1, 0, and then frequency F4 could be 1, 1. So like there are some modulation schemes out there that support more than just ones and zeros, but we don't have to go into that because for Orbital, we only use um, two FSK, meaning two symbols, meaning ones and zeros. So another brief thing that I'll mention is Orbital actually uses GMSK for our satellite, Gaussian minimum shift keying. It's just a variation of FSK that uses a Gaussian filter to create more smooth transitions between these switches between frequencies. There's a bit more information about it in the Comms 101 PowerPoint, which you'll find linked in the previous part one of this tutorial. So you can check that out if you're interested. Okay, now on to some basics about orbital mechanics. So this is important to understand because these are some parameters that you have to input, as you might remember, into the link budget at the very end. So I'm just going to quickly go over what each of the main orbital mechanics elements mean and what they look like. So we have kind of like, there's like six main things to know. This list actually has more than six, but I'll just go through them quickly. So eccentricity is how kind of elliptical your orbit is, very simple. Inclination angle is how much your orbit is angled off the equator with respect to the Earth. RAN or right ascension of the ascending node is basically just an angle from a given reference frame on the Earth, an angle at which the ascending node of the orbit is offset, and the ascending node just means like where the satellite starts to go quote unquote upwards in its orbit. An argument of perigee is where along the orbit the perigee happens, and the perigee is the closest point to the Earth. And basically, it's done with respect to the ascending node. It's like an angular value. So in this case, it's like 270 degrees. Mean motion gives you information about how big this orbit is. It tells you kind of how fast the satellite orbits. Semi-major axis is another version of mean motion. Well, not exactly, but semi-major axis gives like the orbit size, whereas mean motion gives the orbit speed, which is basically giving the same information. Epoch is like a reference time that you can kind of input these Keplerian elements at. It's kind of a snapshot of like when uh, when we're talking about within like the total lifespan of this orbit, basically. Mean anomaly is where within the orbit exactly we are. So like, let's say we're up here, the mean anomaly would be about 90 degrees. The next thing to learn about is TLE data. So TLE stands for two-line element set. And basically, it's this way of encoding information about a satellite and about its Keplerian elements that's commonly used. It's basically something that's given to us typically by NORAD, the North American Defense um, Organization. And that's not the actual acronym. I just kind of just to give you some idea. So they kind of track all the satellites in space, and they give us this information on TLEs, which are two-line element files. And you'll see that like the first line typically contains some information about like what the satellite is. And then the second line contains those Keplerian elements I was talking about. Oh, yeah. And for our satellite, we typically just use the ISS TOEs because we're expecting to be launched from the ISS orbit. Okay. This one is a bit more complicated. Polarization loss. So polarization loss is this idea of how aligned two different electromagnetic fields are. So let's first start by talking about linear polarization. So when you look at kind of any animation of an electromagnetic wave, you'll see an electric and a magnetic field propagating in orthogonal axes to each other. Um, so yeah, the electric and magnetic fields are orthogonal. And basically, this is called a linearly polarized wave. And in order to detect this wave, you might like remember or have a bit of intuition about the fact that the way that antennas pick up signals is by receiving this kind of oscillation in a magnetic and electric field. So the antenna has to be pointed um, towards this magnetic field, electromagnetic field in a certain way to be able to detect that field change. Um, I won't go into too much more detail about that. You can look into like Faraday's law and some things like that that you learned in first year to get an understanding of what that means exactly. Um, but yeah, essentially, so this is what a linearly polarized wave looks like. There's this concept within uh, ham radio about whether your antenna is vertical or horizontal in terms of its polarization. So if you get the chance to play with ham radio on Orbital, you'll notice that when you try to receive a transmission with a monopole antenna, um, if you orient it vertical to the ground versus parallel to the ground, you'll notice a huge difference in kind of the received signal strength. Um, and one direction will like typically give you almost like complete silence in your radio signal, while the other direction will give you like a proper signal. And that's just because the way that the antenna is oriented has a huge deal to do with whether or not it can detect this changing B field. So there is this concept of vertical and horizontal polarization in ground station antennas. Um, that basically means whether or not the electric field is propagating parallel or perpendicular to the ground. So moving on from basic linear polarization, we have this idea of what's called circular polarization. So a circularly polarized wave is one that has an electromagnetic field that propagates in more than one axis. So the best way to explain that is um, imagine this same animation, except what you do is at a 90-degree phase offset, you start to employ like let's say let's focus on this B field here. This B field is propagating kind of within the XZ plane. If we added a 90-degree phase offset, another red wave, another B field that is exactly the same, but it propagates at, again, like that 90-degree phase offset. What will happen is you'll get like an average sort of pointing direction for where the average B field points. And what that does is your B field ends up kind of pointing in kind of a loop instead of uh, pointing like left, like in this case, like along the positive and negative Z axis. It starts pointing like in a circular loop. And that's kind of what this animation is trying to show. I'm sure there are some better animations online that you can look into that might kind of show how a circularly polarized wave comes about. But this is kind of one example. There's also something called an elliptical polarized wave. So you might come across antennas that don't propagate a wave at like the exact 90-degree phase offset. That's just another thing that exists. Another thing is this idea of right hand versus left hand polarization. There's some information here that explains to you like how to determine whether an antenna is right or left hand polarized. But the important thing to know here is when you have two antennas, the transmitting and receiving antennas both have to be the same handedness. Otherwise, they will not be able to receive signals from the other. Okay, so going back to the slideshow, we talked about linear and circular polarization. So one really useful thing that circular polarization does is it helps against misalignment issues. So with a linearly polarized antenna, you're really sensitive to how your antenna is like kind of axially aligned with the other antenna. But with circularly polarized antennas, you can kind of rotate the antenna as much as you want, and you'll still be able to receive the signal. So uh, basically, that's the benefit of using a circularly polarized antenna. The issue is you typically can't use circularly polarized antennas on satellites because they usually look like helical antennas that I showed you before. Um, or there's some like Yagi antennas with radiators on kind of two axes that are used to create circular polarization. You'll actually see that if you look into our ground station architecture at the moment. Um, but anyways, essentially it's hard to get circularly polarized antennas on satellites. So what we typically do is we keep a linear antenna on the satellite and a circular one at the ground station. So you do experience some pretty significant loss in the signal, but it just helps protect against when you're transmitting the ground station being able to receive your linearly polarized signal. And again, keep in mind that the downlink budget is a lot more important than the uplink. So we can tend to accept some losses due to polarization on an uplink. Um, and it's a lot better to have like a much nicer antenna at the ground station for the received end. So that's it for part 2. See you in the next video for part 3.